And then Devesh, you can start.
Okay. So hi everyone. I'm Devesh Karthik. I'm a physics student here at UConn. I just finished my first year. And for the past 2 weeks, I've been working with Jorge on studying the Lindblad Master Equation. And I'll be continuing researching here this summer until around July 12th, and I'll be back in the fall. So, well, yeah, let's get into the Lindblad Master Equation. So there are three main parts to this presentation. First, we'll look at the equation with a brief introduction and understanding some of the background behind the equation. Then we'll look at the Kerr Parametric Oscillator, KPO, in the context of the Lindblad equation and open quantum systems. And then at the end, there'll be an interactive example where we can look at the methodology that we've used, and we'll end with a little problem for everyone to solve. So closed quantum systems are essentially systems that don't interact with an outside environment. They're isolated systems where we can study in theory using the Schrodinger equation, which revolves around the wave function and solving the equation to find the eigenvalues and different properties of the wave function. So we're going to move with leaving h bar as 1 to make things simpler for ourselves. Now, the information in the wave function can also be presented as a density matrix. So we define a density matrix as the cross product of the wave function of each possible state times the probability of that state. And with that, we can get an operator. And in an n-dimensional system, we can use this what's called Fock-Liouville-Hilbert space to represent this density matrix as a vector, which makes our later calculations much more simpler.
Okay, so Devesh, I think let's just put it at a very basic level for the beginning. So the density matrix, as the name may say, is a matrix, right? Which is n by n. So Jackson also is an undergraduate student. So it's a matrix, a big matrix, n by n. So to simplify, he's telling us that to simplify our lives, he's going to put a matrix in a vector, which is going to be n squared, right? Because there are n plus go.
So the dimension will be n squared in the vector, and this makes everything that follows simpler to work with. So some properties of the density matrices. They're normalized, which means that the trace, which is summing the diagonal of the matrix, will equal 1. They're Hermitian, meaning the Hermitian conjugate is equal to the itself. They're what's called idempotent, which means multiplying the density matrix by itself will always return the initial density matrix, however many times you multiply it. They're positive, which means that they have non-negative eigenvalues, so 0 or positive values. And when you're calculating an expectation value, or you're finding what the value of an observable is with density matrices, you can find the trace of the density matrix times the observable, and it'll get you the expectation value. Finally, reduced density matrices are very helpful because what you can do is if you have a density matrix which has 2 subspaces, you can find the trace over one subspace to understand the dynamics of the other subspace. So if I, like over here, if I want to find the dynamics of subspace A, I would trace the entire system over B. It's called the partial trace. And then you would have the dynamics of A. So in closed systems, we can use the density matrix to explore the evolution of quantum states. In the same way that the Schrodinger equation is critical for the wave function, the von Neumann equation does the same for the density matrix. So we can start with the definition of the density matrix and take the time derivative. And then we can substitute the equation. As we take the derivative, we can substitute the equation for the Schrodinger equation. Then we can simplify our output into the product of minus I and the commutator of H and rho. In Fock-Liouville Hilbert space, we can turn this into a column vector, which is our evolution, which is equivalent to the operator lambda, which is an n squared by n squared matrix, and our density matrix, which is represented now as a vector. Now, the von Neumann equation is a linear differential equation, which we can solve in a straightforward manner, and we end up getting the solution presented above. So we can then take our initial state and multiply it by the exponential by raising the lambda to the exponential function, and we get our state at time t. The state at time t starts as a vector, but we can of dimension n squared, but we can map it to an n by n matrix, and then we get our density matrix as we had in the beginning.
Can you go back one slide?
Yes.
Okay. So then you said the commutator, that whole part that is included in the commutator will become that lambda multiplied by rho.
Yes.
Okay. And then you did the derivative of that to get that exponential that you showed to us in the next.
Mhm.
Yeah. Okay. Good. Thank you.
Mhm. So we can map this and get our density matrix again. So this information of the density matrix mapped to an actual matrix is important when we calculate the survival probability, which is essentially an autocorrelation function that can help you determine how different the function in this case, the density matrix at time t is from our initial state, rho naught. And we do that by calculating the trace of the product of rho naught times rho at time t. Now we can look at open quantum systems. In an open quantum system, the principal system is surrounded by an environment, or what's called a thermal bath. And together they make up what we call a total system. We can see the total system is made up of the Hamiltonian of the principal system, the Hamiltonian of the environment, and this term alpha h of I, where h of I is the Hamiltonian of the interaction, and the alpha refers to the amplitude of that interaction, so the strength of the interaction between the system and the environment. So in open quantum systems, the von Neumann equation doesn't work because we can't factor in the effect of the interaction Hamiltonian. So for that, we need to use the Lindblad Master Equation, which presents the time evolution in an open system. So you can see here, we start with something very similar to the von Neumann equation, but then we have an extra term, which is the summation. The summation essentially has the operators L, which are dissipators. These tell us how we lose energy in the system and essentially models the interaction Hamiltonian, and gamma, which represents the amplitude of the dissipation. So we can represent this equation using our previous notation and making this operator, which we're going to refer to as the Lindblad operator, and it also has dimensions of n squared times n squared. It's a very similar equation to the von Neumann equation, and the solution takes the same form.
And we don't know yet what the L is. Right?
Yeah, it's a general operator at the moment that's used as a dissipator. So in our research, we used the Kerr Parametric Oscillators, and we used a Hamiltonian that was used at Yale to create chemical simulators that they used with the KPO. And this is the Hamiltonian that we used, where A dagger and A are the creation and annihilation operators. Then Kerr nonlinearity is represented by K, which tells us which is one of the parameters of the oscillator. Then we have control parameters epsilon1 and epsilon2, and what we call the detuning parameter, which is delta. So a few more details that we had to consider when we were doing research.
Maybe can we go back to that Hamiltonian a little bit? Maybe we should tell people a little bit more about what this is. That there is an experiment behind Oh, no.
Well, at the moment we use only the Hamiltonian because it's based in the previous work in the from people in Yale.
Yeah, but people in this group, like David, Zahir, they don't have any idea about this Hamiltonian. No? So maybe we can tell them that there's a. I know the Devesh already said, but just tell a little bit more that this is a Hamiltonian that is used by this group at Yale to study a superconducting circuit. But why that is so important? Because they are trying to build a qubit, no?
Yeah.
The building block for a quantum computer. And we are trying to work with them to understand better the system. And we already have put some papers with Jorge and Miguel on this, but we now want to include the effects of the environment, and that's where the Devesh is going, right?
Yes.
But this is important. This is the building block of the quantum computer. And the system that they have is very similar to the qubits already available in the IBM quantum computers. They're just doing it a little better. Yeah.
So now we have to consider the environment that we're going to be modeling. So these are more experimental values, the dissipation and the mean photon number in the environment, which lets us experiment with how we want our environment to act. And like we previously had referred to, we have different dissipators. So here we're using the creation and annihilation operators, where the annihilation operator is L1 and L2 is the creation operator. And we can find our amplitudes of dissipation, which we also referred to earlier, by taking these values, which are just experimental values.
Okay, now let me digest this. So there is L1 and there is L2, fine. That's kappa, I understand. I don't understand this mean photon number.
So yes, it's essentially in the environment around us, it's just the number of photons, the average number of photons in the environment that we have to consider that might interact with our system.
Okay, so and if we change this parameter, we can get very different results.
Yes.
Yeah? If we have more photons, there'll be more interaction with the environment.
So here we're going to introduce this value called Tx, which essentially models the decay of the survival probability over time, which we calculated using this method called single value decomposition. And we can see over here, the survival probability is this graph in black, is the line in black, and the blue represents the model that we created using the Tx value, which is the value of interest for the people working at Yale. And that's the value that we were
Okay, so black is exact numerics that you've done in your computer. And blue is a model, it's a method.
Yeah, it's a fit for
it's exponential basically of this.
I see.
The equation for it is down here.
Is that exponential of the Lindblad operator?
Not
No.
exactly. So it's a value that you get by using the single value decomposition on the Lindblad operator.
Okay, so it's a method that you use.
Yeah, as Devesh said, the Tx represents a quantity that is provided by the Lindblad operator using this method, the single value decomposition on the Lindbladian. And the black line is the survival probability with the environment.
Okay, are we going to learn about this single value decomposition method or not?
At the moment, no.
Okay, we're just using.
Yeah.
So maybe you should consider a log-log plot for this figure, no?
How did you manage to get the blue curve? You did something.
Yeah.
The blue curve is explicitly the exponential of this Tx, and the Tx is provided by the Lindblad.
Okay, so then the blue curve is just a fit.
Yeah.
You didn't do this method.
No, but using the Tx, that Tx is something that is from the Lindbladian.
So we get the Tx from the Lindbladian using this SVD method. So we extract the value from the Lindbladian.
Okay, look, but those guys who use this method, they did something that we are going to learn someday. Okay, but if I look at the plot, blue, you put there exponential minus 2 pi t over tx. So this is the tx that you're fitting.
Yeah.
And you go to the blue curve.
Yes.
Or the,
No.
the TX came from the method.
Yes. TX came from the
Ah,
method.
I see. Okay,
And
so
the
it's
black
not a-
curve is the survival probability.
Okay, so it's pretty close, huh? Although it hasn't decayed much.
Yes.
May I suggest something, Leah?
Well,
Can you hear me?
Yes.
Someone is asking something there.
Yeah, Jonathan is asking something, or maybe suggesting something instead of asking something.
We
But
cannot
what if
see
you
Jonathan.
consider, can you hear me? No?
We
Leah,
can,
can you
but
hear
it's
me?
very low, so maybe I have to put it up the volume. Just a second. I'm going to put it up. Maybe the best. Can you
Yeah.
mute you?
Can you hear me? Yes.
Yes. Now
Okay, I can hear your echo, Leah. Okay.
now it's not anymore.
Yeah, a lot of echo. Okay. Still echo. Okay. So now, my suggestion is if you consider here log scale instead of linear scale, both in time and in the survival probability, in order to see just if you want to show the difference between the two curves, I think you are going to have a better view from this log scale. No, I mean this is the usual thing that we do. Consider a log scale. Yeah, that's it. I don't know if what I said was clear, or can you hear me? I don't think so.
Well, Jonathan, I can hear you, but
I can hear
I
you,
don't know.
Jonathan.
Yeah,
I think it's them that they can't hear you,
Yeah.
but I can hear you, and what you said is very
I can
sound.
hear you.
Okay.
okay.
Could you hear Jonathan?
Yes, he told us to do a log plot,
Yes.
Yeah,
yes,
that's it. Yeah.
and we agree.
that's it. Mhm.
So essentially the main point of this is this value which is basically what we've been studying for our time, and we look at how manipulating different parameters affects this TX value. So first we look at manipulating the epsilon1, epsilon2 control parameters. We set delta equal to 0 and the Kerr nonlinearity to equal 1. And this is the resulting Hamiltonian. So this is the graph that colleagues at Yale are working on right now. And they came with this map. And we can see that they have the plot of the natural log. It is a log plot of the TX value. And you take the control parameters. Yes.
The survival probability is independent of the initial state,
Or
no?
No, the survival probability depends on the initial state. This is for
Or the TX is independent.
yeah, the TX is independent. It's
But the survival probability
yeah.
is not.
TX comes directly from the Lindbladian operator.
The Devesh and so these solid lines are is the log TX, and the colors is numerics.
Yeah, the solid lines. You mean like the contour lines?
Yeah, okay, because there are some black lines and
Yeah.
there are some colors.
So the colors represent the log TX, and the
Ah.
black lines are the contours, drawing the difference between them. So this is the graph from Yale, and we reproduced it
But-
like this.
Okay, so we are only showing the results of the TX. We are not
Yes.
showing the numerics.
Yes. We look at
What about your?
We are only showing the blue curve on the first plot that we had.
yeah, we're not looking at the survival probability, just the TX values for different
Right, yeah,
Yeah.
fine.
values of epsilon1, epsilon2.
And then I have another question. Okay, we're just showing TX, so that's Miguel's question. Fine, I understand. Okay.
Yes.
I don't know. I don't know how you calculate TX.
Yeah, okay. So
So
there's I'll try to explain it, but I don't fully understand how this SVD works myself. We're still looking at it. But there's a function called the SVD, which takes the value of a matrix, so we feed it the Lindblad operator. And it takes some value from that matrix, calculates something. And that value that it outputs is what we use to get Tx. I think we take the minimum of the reciprocal. So we take all the values and we take the reciprocal
Mm.
of the SVD. And that's how we get Tx. We take the natural log of that, which is our ln of Tx.
Okay, people who are in the audience there, Kuro and Edwin, you may know, or you may want to know about the single value decomposition method, huh? You can help us.
Yeah, I think that it's in most literature it's called singular value decomposition instead of single value. And I think here we are compelled to use singular value decomposition because the Lindblad operator is not Hermitian. So we cannot like diagonalize it to get eigenvalues and eigenvectors, but instead we can get the right eigenvectors and left eigenvectors, which is like generalization of the usual diagonalization we do for Hermitian Hamiltonians. And I think these singular values are somehow fed into the Tx operator, but that I think Devesh will explain us how to construct these Tx operators from L1 and L2.
Edson may also know or want to learn about this, right? Edson Miguel, because of okay, go on, Devesh.
Okay. So another thing that we found is that there is this white line, which is described by this equation on the screen. And above this line, we see that for each point on the graph, which is for each epsilon1, epsilon2 value, we find that there are 3 critical points per point. And below this white line, there's only 1 critical point for each value. And we think this is something important, because we also see that this curve almost models the shape of the darker colors on the contour grid.
I have a question to you two. So this 1 versus 3 remains if you change the parameters also. 1 critical below and 3 above. Always like that. Always this line.
Yes.
Okay.
Yes, this is only for the closed system, the white line.
Yeah, the white line came from the closed system.
Yes.
But you're now doing this exercise for the open one, and this white line always separates the colors like that.
Yep.
Okay.
Yes, we get the white line from the classical Hamiltonians.
Yes, exactly. And the equation is given in this form.
Right.
It's analytical.
It's an analytical equation separating these 2 regions.
Yeah.
From the class.
So next, we also looked at varying delta and epsilon, which is also known as the Exciton polariton model. It gives us this Hamiltonian over here.
Okay,
So now we are studying a different system.
Yep.
The Exciton polariton. Okay.
May I ask something? Sorry, excuse me.
Just a second, let me turn up the volume.
Okay.
Say.
Yeah, could you repeat please what is the meaning of T sub x? I mean, Tx is the decay rate of the survival probability?
Yes.
And this was extracted numerically from the Lindblad Master Equation?
Yeah.
Okay, that's, thank you.
Yeah.
You can go.
Yeah, so this is the Hamiltonian that we get, and we've modeled, once again, the natural log of T of x.
Okay, but let's just tell people a little bit about this other model. This is a completely different thing. Has nothing to do with what the people at Yale was doing, no? But there is another group of people with this other kind of system also thinking about building blocks for quantum computers.
Yeah.
And this is what Devesh is calling the Exciton polariton system. Okay, so you see the Hamiltonian is different, but it has some terms in common.
Yeah, basically cancels the value of epsilon2.
Epsilon2 is no longer there. Okay, go on, Devesh.
So for this graph specifically, we used the value of epsilon1 equals 32 instead of varying both. And we took the delta value over the delta critical value, which we calculated based off the epsilon one value that we chose. And what we found is that the critical point and the sudden increase in the graph happens around 1.
But this is very nice.
Yes, I think that we can include also in the
This is very nice.
because it is so important in the open system. This quantity also detects the criticality that we know in the other quantity, the
Okay, so
quantum sensing.
what Jorge, I don't know if you guys can hear, but what Jorge is saying is that he had already studied this model that Devesh is showing closed, and he had found this critical point.
Yep.
Now he's doing the open case, and again, the same critical point shows up. So opening doesn't change the, okay, go on, Edwin, what do you want to say? I'm going to raise the, go on.
So what does the critical point imply in this model? Like what happens on either side of the critical point?
Oh, can you hear me, Edwin?
I can hear you.
Yeah,
I can hear you, Jorge.
Okay. Yeah, in this system, the critical point becomes in the classical sense and is represents an excited quantum phase transition for a specific critical value. I think that, well, maybe in this slide is not exactly the delta C. That delta C is the critical parameter that is in terms of epsilon 1, Kerr, and delta. Well, no, and Kerr. Yeah, exactly. So it's a quantity defined by a formula in terms of the other parameters, and in this sense is more or less similar at the previous model, that the system passed to have a single minimum to pass to 3 critical points. But the nice thing in this system is that the other 2 critical points that are new are only for excited states or excited levels in the quantum sense.
So you're saying that only at the first critical point the ground state properties are changed, but in later critical points your excited eigenstates have different properties on either side. So I mean, what is those differences in the properties? Like it is from superradiance to some other phase, or what is happening in terms of the ground state properties?
Yeah, maybe we can think in this kind of change of phases, because, well, yeah, well, I'm not sure about the correct name to say about this new phase, as you said.
Okay, it's something different you're saying. Okay, sure. Yeah, please go on. Yeah.
It's not
Thank
super radiant,
Yeah.
but what Jorge had seen, maybe later or another day we show to you the classical phase space.
Yeah.
And then is what is changing. There's some like a saddle point shows up, right?
Yeah.
A local maximum shows up, things that didn't exist. And apparently this transition is not affected by opening the system.
Yes, exactly. This is the main result that Devesh.
So that's the stability of your qubits.
Yeah.
Yeah.
We are thinking about using this system
On quantum sensing.
for sensors, yeah. So it's the stability of the sensors to environment. That could be interesting.
Yes, exactly.
Oh, wow. Yeah. Please go on.
System or the anticipation?
This is with dissipation.
With dissipation, what is the anticipation about?
They are the same in the previous.
Is this kappa? No,
No,
this
this
kappa is
is-
the care, which was the other.
The previous.
Yeah, hold on.
Sigma or the?
Point one.
Yeah.
Yeah, it's
but-
0.1, it's small.
It's not. It's
Small compared to the care.
Yeah.
okay.
Well, I don't know if things get affected by this.
Maybe, yeah. It's a good question for the experimental people. But I think that is a small respective curve. Yeah. I think that is fine.
It's not.
In the case of the guys in Yale, they plot epsilon 2 and epsilon 1 and epsilon 2 in the range from 0 to 10.
Okay.
And they use the same parameters for kappa and eta.
Mhm.
Okay, but what this is important. If
Yeah.
we are going to talk about being
amplitudes.
stable,
Yeah.
robust, we need to know robust up to which value of the
Sure. Yeah.
coupling parameter. Okay, go on the bash.
As I mentioned, the critical point happens around 1, and we can move on to the next part. We're going to look at a little interactive example, which we got from this journal over here with some help from Isaiah and Jorge, who looked at the example and worked through it first. And I think it'll help us better understand the process that we went through to get the different values. So this is the Hamiltonian that we're going to be looking at, the 2 pi over 10, and that's the poly x gate. And we're going to start with the initial state 0. And the dissipator that we're using is 5 pi over 100 times the poly x gate. So
wait, so if I wanted to
Think about this as those L's, I would say that the L is a sigma X.
Yes.
Okay.
yes.
Yes, this is the example that they use in this paper.
Ah, okay, thanks.
I wonder if I can share this part of my screen now. Moving around a bit. Does it show my whole screen?
Yeah, I see here.
Okay.
I see the different ones.
Yeah.
But not the other.
Oh, is it?
Yeah, move. You see?
Yeah,
It's
move
on the
the
corner.
other
Yeah,
window.
it's
Yeah.
in the
No,
other
but then
direction.
you cannot see on your screen.
It's fine. I can look up there. Yeah. So
Wait a second, guys, because I think here people are not seeing.
really.
Do you see a curve? No, right? Like a sinusoidal curve?
No. I can.
So,
Oh, okay. I can
Maybe
just
you can
share the
jump
screen.
to
Yeah,
the-
I can. I think it should work now.
Yeah.
No.
now see.
Yeah. So I can. Yeah. So we're going to be using again these values.
Wait a second, I want to be, because this is going to be.
This
Yeah.
is going to be our homework.
No, we're going to
This
work
is
through
not-
this.
Okay. Yeah, I want to take notes, but okay, so it's the sigma. Can you go up again? So the system is sigma z. Initial state is 1/0. Where is the environment? Also sigma z?
Yes.
2x.
This is the example.
Okay.
But why then are we showing sigma z there? I don't understand. The system Hamiltonian is sigma z or sigma x?
Sigma x. Where?
Okay, so system Hamiltonian is sigma x.
Yeah.
And the C0 is also sigma x.
This is some.
And what is this E0?
Well, I think it's one way to represent and that is I'm not sure.
Okay, I don't understand what is the total Hamiltonian of this system, but maybe as you proceed.
So the total. You mean like including the environment? Okay.
Because I don't understand what C0 is.
Okay. Yes. So C0 is the dissipator. This is like in the previous one we used the creation and annihilation operators. For the L1 value and the L2 values were equal to A and A dagger.
Fine, okay, so then it looks like the system, the Hamiltonian that describes the system is sigma x.
Yeah.
And the L's in that Lindblad equation are also sigma x.
Yes.
Fine. And we are going to adjust the coupling parameter, that gamma that you had before.
The
Or kappa.
kappa. Yes, we're using fixed kappa that we determined. I'll show
Okay,
you.
let's see, let's go on. See.
I'll move the screen too. So we're using this package that Jorge created.
Okay, from here, maybe we can understand better.
Maybe you can increase a little bit.
Yeah.
Size.
At the bottom, 100, yeah. Okay, Hamiltonian polymatrix 1, C0 polymatrix, fine. Then GS is what? And CS.
Sorry, 1 second. I'm just trying to make it bigger so people can see. Sorry, what were you saying?
What is GS?
GS is our gamma, so it's the amplitude of
Is the
dissipation.
yeah, okay. Okay, fine.
So this is, we're going to construct the Lindbladian, putting in all these values. So this is how we create the operator using the package that Jorge created.
And why there is a number 1 at the end of that bracket?
This gives us the H bar value. We're just setting
Uh-huh.
H bar.
Ah, okay. Fine.
So now what we've done is we've taken the Lindblad matrix, the operator, and we've put it into a data file that's saved onto the hardware. And if we want, we can continue in Mathematica, or we can take that data and we can move into a different language as long as you import the data file. So I'm going to be working with Python because that's just what I'm most familiar with. But I can show the data file.
Yeah.
No, careful because that second line, there is an extra N, blood.
Yes, so that was to return the data. So that's the matrix version to call the matrix. And if I was continuing with Mathematica, if we wanted to call the matrix and look at what it looks like, I can show that right now.
Yeah, but I don't understand how the name has changed. Before
Yeah.
it was blood, and now
So
you
that's
want
so
blood. Then
Lindblad is to create the operator, and Lindblad N is to display it.
oh, you just need matrix form to display.
No, well, so the first code, Lindblad, with these parameters, the age, the Hamiltonian
Uh-huh.
operators, is
Is the code that will give you the matrix.
and also is to return the file that has this information that he will show. And Lindblad is if you want to continue work with the Mathematica, for example, yeah, here run the code, and this quantity is the Lindblad.
Okay.
For this case.
I'll ask you later. Fine, because I didn't see in blood defined anywhere. So how can Mathematica know what in blood N is?
Lindblad
It's somewhere defined.
is
From the package.
the
From
matrix.
the package.
Yes.
Okay.
So yeah, this just so to restate what this does. This creates the Lindbladian and a file, and it creates a data file, which I'll show you. It doesn't save the matrix itself. Lindblad N will call the data file and portray it as.
Fine, I understand now. But now Devesh, so this is the black box that Jorge gave to you, right?
Yeah.
But this is something that you haven't learned how to do yet.
No.
But you should, yeah?
Sure.
Okay.
And I'll show the data. This is how the data looks like. It's in a DAT file if you open a text, and it saves each value of the Lindbladian just in a list like this. We have the real part, and we have the imaginary part as well. And in Python, I'll be able to turn this code into a matrix.
Mhm.
So I open.
So now we go to
Python, yeah?
Zoom this in. Oh. Run our imports.
Okay, so then we have the system that state 1, 0, fine, and then you created the density matrix. Now the Lindblad, you're going to from Jorge's code, all right?
So this is just, we define our initial state. This is a function that I'll call later. I write the function. It basically just reads the data is all it does.
Fine.
So if you put in the data through here, I convert the things so that Python can read it. And then We just take the data and convert it into usable information.
Okay, so you brought that and now you're going to create that exponential. And that is the part that you are solving. Now you're evolving the system and computing the survival probability.
Mhm.
Sorry, no,
Of course. So yeah, we solve for row at this time that you can input, and it returns the value. You take that's the exponential function for exponentiating a matrix, and we take that with the product of the initial state, and we use the reshape function to map it to a matrix like we've discussed before. And this calculates the survival probability, which is the product between the time and the initial state. And we take the traceable, of course. So we can run this as well. So we read the file and then we can create the Lindblad again, and I can show you what the matrix looks like here. This is what it looks like. It's not as readable as Mathematica, but you can see the first value is the same as the first value here, and so on. Next, we're going to calculate the survival probabilities.
Then you read the prompt through.
Oh.
Yeah.
Yeah.
We have the definition of DT.
Yes. Yeah. Hmm. It was there last time, right? Yeah. That's
The number is facing.
No, I think the function name is I have it in a different file.
What is the name? Don't you know?
Space. I was trying to remember.
Without the D.
Yeah, without the
Just
D,
space.
and you need to give the niche of the file and how much
And this,
Yeah,
yeah,
you need, like 100 numbers.
Yeah.
Yeah.
So
that's
I
what
think
it
it's
is.
yes.
yeah.
Thank you.
Oh, wait a second, there is a question.
Yes.
go on.
Yeah, so the Lindblad operator seems symmetric, right? Is there a particular reason for that?
Symmetric.
Looks symmetric. I'm not so symmetric, but maybe for this case. I don't know.
Is it because the dissipator is the same as the Hamiltonian?
So can you show the Lindblad again, Devesh, please?
Show the mathematical one because it's easier to see.
Ah, it's symmetric. Yep. It's symmetric. Yeah. For this case, it was symmetric.
It's not always symmetric.
It's not always.
Is
So they're saying it's not always symmetric. Probably it's because it's sigma x, sigma x.
Yeah.
yeah, so that was another question. Like here, the dissipator commutes with the Hamiltonian, like our correlation will work, right? So, is there any particular reason for that, or is just exercise?
Yes, just we use the example that Isaias was studying a little bit because it's in a two-dimensional problem, and it's easy to show the matrix, the structure of the dissipators. But the homework is a little bit different.
Nah, they will give us
Okay.
the hardest part.
Sure.
Sure. Okay. Thank you.
So yeah, calculate the graph of the survival probability now that we've run the values.
Mhm.
For
Maybe we should put more
15.
space.
Yeah, so we can
Smaller
change.
space.
So for this is the space that they showed us, or the range 10. But if we look at this from a wider, so I will change this to this one down. This to
Ah, so there is
Yes.
a decay there because before we didn't.
So there is a decay there.
So you can see that the oscillation starts small values of 10, but it gradually decreases.
And so this depends on that gamma that you chose, right? If you would put the gamma that you chose was 0.1, was 1. The-
Gamma was 1.
Can we check? Can we put 5 or 10? So keep this in your mind. 400 is when it was.
Yes. We change this.
Or 10. You mentioned.
Two.
So he still calls you mathematical because you don't need to run the mathematical.
No. Yeah, maybe he forgot a little bit, just how to import the package because
Oh,
it's
yes.
from the beginning.
So
So
they will change now, huh?
yeah, because no, the package actually was
Yeah, well, all because that's how he got it. So every time, I don't know. I see.
yeah, but then for the beginning he import the package that is in the
Okay, so then we go back to Python.
Yes. I'm just copying the data file.
But we need to do this, the whole thing in Python. Doesn't make sense to be extracting.
yeah, or well, actually, for example, in the case of the Kerr oscillator, we built the Lindbladian without numerical in the symbolic sense, and he imported the symbolic file in Python once, and this was
Yeah, but it should not import anything. That it should be a self-contained code, I think, right?
So this is what our changing the 5, changing to 5 looks like.
Did it change the values because okay, before it was 0.25 and now it's 0.025. I see. Okay.
And yeah, I can compare it.
So that will make it things faster. Yeah. Okay, it's 10 times bigger. So that will maybe 10 times faster. Let's see.
Let's see. Just rename it. Import it. Reconstruct the Lindbladian. These are all.
0.0025.
Yeah.
Okay, so then everything makes sense, right? Okay, good. That's what you wanted to show us?
Yes.
And now let's do a homework.
Yes, that is, we'll go back to the presentation. So this is the exercise.
Wait a second. Well, you're going to share this with us, right? This Hamiltonian, the slides. Okay, so I don't need to write it down them. Okay.
and the codes, of course.
Okay, and this will be our tutorial, or you have a written tutorial with words and no, this is just the slides. Because we can write a tutorial, right?
Okay, yeah, I
With
can-
explanation and all.
We can do that. We don't have one right now.
So that would be a nice, okay, so then go on, sorry. We have the Hamiltonian.
So we have the exercise is to graph the survival probability from 0 to 10 of this Hamiltonian. And we're going to use dimensions of 15 with the dissipators A dagger and A.
So L1 is, does this make any difference? L1 is A dagger and L2 is A, or? It is.
Um,
No, it's the opposite.
maybe we need to call the L1 is A.
L1 is
Always.
L1 is A and L2 is A dagger.
Yes, because in this sense, the gamma is connected with
Right.
A,
There's
gamma
gamma 1 and gamma 2.
Yes.
Someone raised their hand.
Alexandre, just a second, Alexandre. Question.
And hi, Devesh. Just a question. What's the motivation for choosing these dissipators? Which other kind of dissipators, for instance, could we choose in this? It's related to which physical situation. What's the physics of the choice of this dissipator?
That would be good to understand better, right? Well, in this case, I think it could only be combinations of A and A dagger because that's the only thing we have in the Hamiltonian. Now,
But the physical is more like
if
that
it's
is the
dephasing, if it's not.
what is the creation and annihilation of one single photon in the interactive part.
Yeah, it essentially models what you were mentioning earlier.
Maybe I don't know if it's possible the environment can change phases or not. I don't know if it's possible.
It's usually there is the system, the environment sucks a particle out or puts a particle in, no? And here probably it's sucking more than putting in. That's maybe why there is a difference in the gamma 1 and gamma 2.
Yeah, this is about the parameters and about the operators. I think that is because it's the creation and annihilation per particle, as Leah explained.
You just see this, the gamma 1 is kappa n plus 1 and the gamma 2 is
Because sometimes in other works I seen that people use A dagger squared or A squared, etc. I think that depends of the
yeah, but look, sorry, but if you look at gamma 1 is associated with A.
Yes.
So it's the destruction, and you see that the strength is of the order 0.1. But gamma 2 is the one that then now the environment is putting something in the system, and then this is the order of 10 to minus 2. Because it's 0.1, 0.1 is much smaller. So the environment is just taken out.
Yes.
But there are different ways to model these things.
Yes, I think that it exists other possibilities.
Here is just putting and removing particles. But like in the case that Isaias is doing, and the other one that we saw is dephasing, I think. The sigma X, sigma Y.
Yeah. Okay, so thank you anyway.
But these are good questions, and we need to understand very well the things. Yeah. Go on.
Because the equation that you use is for a thermal bath. The interaction with the thermal bath is with photons. And the unit interaction that system with the bath between the
is per photon.
Per photon because the system is
Yeah, that eta, which is the average number of photons that Devesh was telling us, it's like related to the temperature of the bath.
Yeah.
You could make it much hotter, probably with more photons, and cooler. No? Okay, so these are also nice things to go on. Okay, but let's see our problem. Go on, Devesh.
So essentially, these values to create the operator using Jorge's package. And then like we did, we can export the data file into whatever you want or continue in Mathematica and graph the survival probability from 0 to
I have a question. So now we have every constant defined, and how do we use, I mean, gamma 1, gamma 2, is it we use the package to plug those values in?
So gamma 1 and gamma 2 will go into in mathematics a variable called GS. It's a list variable. And in that, each gamma value in order should go with gamma 1 and gamma 2.
Maybe you come back at the open that one.
Although it would be good for us to try to write what Jorge did. Otherwise,
s-
we, at least the postdocs, we should try to do what you did.
the package.
The package, right, of course.
Yeah, sure. It's the-
Okay, the first step is, okay, we can just use your package and try to do what Devesh did, but then we have to do it on our own, right? The whole thing.
I think that, well, I use especially Mathematica because I optimize the symbolic properties just to factorize the coefficients in the multiplication and commutator and anti-commutator process that is in the Lindbladian per definition, independently of the number of dissipators or the Hamiltonian size.
Okay, you did it symbolically.
Yes, all this symbolically.
Okay,
We can pass, for example, in Python, that also is possible just to use the SymPy package, as I understand, and we can pass the code.
but we don't need to do everything symbolic. No, we can put in the beginning of the code, what are the values of our parameters, run it, because it's not an enormous matrix.
No,
it's-
no, but for the homework, yes, but in our, well, in a big system, it's,
You don't want to run it.
because you're doing large dimensions.
Yes, but also, so if you have a dimension of n, right? Your Lindblad is going to be n to the fourth.
Mhm.
So it's a really big.
So you don't want to do that part of the Lindblad every
yes,
time.
because
I
the
understand.
Lindbladian has n at the 4 components.
Mhm. I see,
It
okay,
was a problem.
I
Because,
see.
for example, just to build the previous map that Devesh showed, he used well, I don't remember the resolution of your plot, but
The resolution is 50 by 50.
it's 50 by 50, but per point, he needs build the line.
So if we
Big
run the
dimension.
mathematical code for 2,500 times, that'd be very long.
Yeah.
So what we did, it still took a while, of course, but what we did was we took the data from Python, like we showed. But when we imported it, we left it so that there are variables in the data.
Exactly, and it's
So
the
when
main
we
thing that,
read through the file, we replace the value in Python.
I see.
yeah. In
I
this sense, we built the Lindblad and in Mathematica used to be symbolic,
To have
and
the
after only replace the values.
So you don't have to
Lindblad
build it again.
could be Python, Fortran, Julia, etc.
Okay, I understand. Fine, but if you had to run just once,
Mhm.
you
You-
could do,
yeah.
and you know how to build the Lindblad.
Actually, no, this.
But you will learn.
Yeah, he
Okay,
will learn.
at least once, yeah,
Yeah.
numerically.
Yeah, numerical too.
All right, go on.
So with these values, this is the Hamiltonian, these are the. But yeah, so we can put in the gamma values to GS over here. So right here it's just 10, so you
One, whatever.
Yeah, could be numerical something.
Okay, so you're going to share these codes with us, otherwise we cannot do that, yeah?
gamma 2, and then this would be your equation relation operators. Would be L1, and exactly would be L2. This is just the dissipator, which was previously defined. And then Hamiltonian book.
Yeah. Do you have the code that is useful for the homework, maybe?
And now all these definitions, A and A dagger, it's from your code, right? So we have to have some explanation.
Yeah, but
That-
yeah,
You have,
we
okay.
have.
Losing them.
Okay. Something happened. Yeah, so you're already seeing the troubles that you're going to have to Make everybody see. Okay. So we have there what are the symbols. Okay, so then we know what to put in your Python code. No,
No,
in the Python code we just call this. Oh yeah, there. The CS and the GS. Okay, so I think this is very nice. Maybe I'm going to stop recording, yeah, because yeah.
Yep.
But okay, I don't know if anyone has any question, but I wanted to give some suggestions. I'm going to stop recording.